In this section, let's take a look at the init process within the Red Hat Enterprise environment. The whole boot process, in fact. So currently the BIOS is scanning the hardware to see that the devices that are connected are functional, and presuming that they are, will turn over control to the Grand Unified Bootloader, or GRUB, or whatever bootloader you happen to be using. In the case of Red Hat Enterprise Linux, it defaults to the GRUB bootloader, and if it's the lone operating system on your system, then it will almost certainly be GRUB. So all the hard drives have been checked. Now we'll get the boot menu. And we've interrupted the boot menu to discuss a little bit more of the handoff. So the BIOS has checked what it needs to check, which includes the memory, the clock, as well as connected peripherals, including optical drives, floppies if necessary, and otherwise it also checked the fixed storage, which for this system happens to be SCSI disks connected to a RAID backplane, and those all checked sans error, which caused the BIOS to search for the master boot record, which is a 512-byte sector on the first hard drive, or the first bootable hard drive, or the bootable hard drive. So depending on which drive you have defined in your BIOS as the bootable drive, the master boot record, or the MBR, is consulted from that particular disk where the operating system bootloader should be found. Now for our case, that bootloader happens to be GRUB, and this happens to be phase 1. Phase 1 is 512 bytes. As we've shown you in the /boot directory, the 512-byte phase 1 GRUB bootloader is the code that's stored in the MBR. Once that code is referenced, its sole job is to invoke GRUB phase 2. Phase 2 provides support for the various file systems supported by Linux, including ext2, ext3, and ext4. It's important to note that Red Hat Enterprise Linux will provide boot support for ext2, 3, and 4 using ext2, which means there isn't journaling support for booting, but eventually when the operating system is fully mounted, then journaling is enabled, which means you won't lose any transactions. So just the boot process alone loads sans transaction support, meaning without journaling. So the fact that we're able to make a selection and begin the loading of the kernel and the initial RAM disk is the phase 2 section of booting. Now if we interrupt this process by supplying the password and editing the lone entry, we see, as mentioned, various items on the list, which includes where GRUB expects to find the operating system on the first hard drive on the first partition. And there's actually a translation table, a mapping file in /boot, which we'll take a look at once we bring the system up, which translates HD 0, to a dev location for our system, dev SDA, or dev SDA 1. So GRUB knows where to find the operating system based on this particular specifier. Then it knows where to find the kernel, which happens to be 2632 VM-Linux, which is in the boot directory. It's also important to note that the paths that are referenced here are all relative to the /boot directory. So when your system is up and running, if you navigate to /boot, the files that are in there are the files that are referenced using / from the GRUB boot menu. So this isn't the absolute path from the top of the tree. This is the path relative to /boot without actually explicitly listing /boot. So the kernel's loaded with a number of options. Initially the kernel loads the root file system in read-only mode, and also extracts the initial RAM disk, provides support for storage and other connected devices. It queries the system, it checks the keyboard, connected devices, optical, storage, graphics, etc. So it sets up the system and then remounts the root file system in read-write mode, and eventually hands over control to init. So just to back up for a second, you start your system, the BIOS fires up, and if your system battery is fine, then the time will not have changed since the last shutdown, and the BIOS will check your hardware successfully and then search for the MBR on the first bootable disk. So it's BIOS to bootloader. So BIOS then grub loads its phase 1, whose sole purpose is to load phase 2. Then phase 2 gives us access to set up our Linux environment, which includes loading the initial RAM disk, that's the init RAM-fs, and the kernel with the root file system in read-only mode. And this is done with ext2 support within Red Hat Enterprise Linux, as opposed to ext4 or 3 or otherwise. Once the kernel and initial RAM disk have been unpacked and hardware has been detected and the kernel has been remounted in read-write mode, then the boot process is handed over to init. The init process is the first Linux/Unix process that's responsible for spawning all subsequent processes, which include all of the user space processes that we use, including, but not limited to, background services like SSH, MySQL, your MTA postfix, for example, or the GNOME desktop environment, the X11 environment, the graphical environment for that matter, and for setting up the run levels, which basically associate different background services and foreground applications with various levels. So for example, if we boot the system to single user mode, init knows not to set up the networking environment, but provide us with a single shell that gives us access to the mounted file systems. If we boot into run level 3 mode, for example, that's multi-user mode, the system's connected to the network, people or users on the network may connect to our system using an accessible service such as SSH or MySQL or Apache or, let's say, postfix. And if we boot to run level 5, then all of the services from run level 3 are invoked, plus the graphical environment, which gives us the graphical desktop. Defaults to GNOME, but could be KDE if you've configured as such. So the run levels that you most likely will use within Red Hat Enterprise Linux include 0, which halts the system. In other words, when you issue a shutdown command. 1, when you're performing administrative tasks and want exclusive access to the box, meaning no connections from the network. 3, multi-user access sans graphics. In other words, you'd like the server to boot, but don't intend to use it graphically. In other words, it's going to process services in the background with little to no foreground connectivity or interactivity. Or 5, where you want everything, all of the services or the advantages of run level 3, plus graphics because you intend to administer the system graphically. So, and 6, we should also note when you intend to reboot the system. So you are most likely to interact with 0, 1, 3, 5, and 6. 2 and 4 are also available. They're also multi-user, but they're unused. They are there to allow you to customize them accordingly. And in many application scenarios, like appliances, for example, that rely upon Linux and other Unices, run levels 2 or 4 are often used for customized applications. I've worked with many firewalling devices, for example, that use run levels 2 or 4 to boot the system based on perhaps Red Hat, Debian, or some other strain of Linux. So, as it stands now, let's boot into run level number 1 and describe in more detail how init, in conjunction with upstart, starts your system. So, we'll go ahead and edit this entry. Now, there are 2 ways you can boot to single user mode. You can either indicate the numerical value 1 or type the word single as we've been doing. If you enter 1, the system knows to boot into single user mode. You may also specify the numerical values for the other run levels, 3, 5, 6, or even 0 to halt the system, for example. So let's go ahead and try to boot. And here we see the services loading, and now we have access to the system. Notice it reads above telling init to go into single user mode. So if we execute run level, it will reflect that we're in single user mode. So let's psef. PS is a process listing application. grep init Init is the first process. Notice it has a PID of 1, PID 1, and it's reliant upon PID 0, which is the kernel or the scheduler, which launches it. So init is the first process, and in Red Hat Enterprise Linux 6, that's handled by the upstart package. In fact, if you get rpm query all, which is the utility used to query the package's database, and search for upstart, you'll see that upstart is a package. And if we list the contents, it includes everything, including the init items and the help files and so on. So let's pipe the output to less to look at it one page at a time. And notice that it includes etc init, which is an important directory, which includes config files that are referenced by init. It includes an upstart.conf file under dbus, system.d. It includes some key binaries such as halt, which shuts the system, init, init control, power off, reboot, etc. A number of key utilities are included. The packages that are included with prior versions of Red Hat Enterprise Linux's sysv init package are now rolled into the upstart package. And upstart is an event-based manager of services, which is more like an object-oriented way of managing services. So as events occur on the system, upstart can interact with those events and start or stop programs accordingly. So it's a more object-oriented or natural way or a natural approach to managing services, and that's the new upstart method. But a lot of the old techniques are still in place. So for example, let's take a look at what happens. So as we've mentioned, when you turn on your system, the first thing that loads is the BIOS. Then there's a handoff to grub, which loads phase 1. Then there's a handoff to grub again for phase 2. Before we move on from this, let's just take a look at where this all takes place by navigating into boot. So the BIOS starts up, and in the grub directory, notice that there is a 512-byte stage 1 file. This is the handoff file, stage 1. Let's do an LSL stage star. Stage 1 is consulted first, but notice that stage 2 is considerably bigger than stage 1. Stage 1, it's roughly 5 times 10 to the second. Stage 2 looks like it's about 113,000 bytes, or roughly 1 times 10 to the roughly fifth or so. So it's a considerable difference in sizes. But remember, that difference is important because the legacy PC platform, for which we still support in x86, is restricted to a 512-byte MBR. So that's why bootloaders like Grub still include support for the 512-byte MBR, because that's how PCs boot, unfortunately. So stage 1, stage 2, it all happens quickly, so it's not so important to us, but you should know as an administrator how this all works. So stage 1 is called, then stage 2. Now within stage 2, there's support for the file systems that you see above for loading various file systems. Notice, for example, ISO 9660, which handles optical media. There's FAT, and there's also EXT support, which causes the file systems like EXT2, 3, and 4 to be loaded with EXT2 support. And then there's also a grub configuration file, which contains the menu items that we see. Well, there's one menu item, so the menu item that we see, the default is set to 0, and 0 is this first item that you see, which includes the MD5 encrypted password to be able to make changes to the menu item. But it loads this kernel as well as the init ramfs file. So BIOS, again, to grub, which includes phases 1 and 2. And then from grub, the handoff to set up the environment, and that's via the initial RAM disk or the init ramfs, which then hands over control to the kernel, and after the kernel mounts read-write, then hands over control to init, the first process, which then spawns the various processes, foreground and background. Now when init starts as PID 1, as we've mentioned, let's psef grep init. You'll see that init is PID 1. It's PID 1 on all NIX-based systems. But notice that it was invoked by PID 0. That's the kernel, the scheduler. The scheduler within the kernel loads init. So in our hierarchy here, the initial RAM disk loads, it sets up the kernel, the hardware is detected, and the kernel then hands over control to init. So the kernel is responsible for the invocation of init, which is why there is a preceding process ID of 0. Now when init starts, it consults a number of things. Let's take a look at some of those things. We'll navigate into etc.rc.d, and in this directory are a number of files. System initialization takes place by consulting rc.sysinit, which initializes the system, makes it available for all run levels. So it contains a number of items, setting the hardware clock, for example, initializing the keyboard, storage, you name it. There's some basic or common denominator checks that have to take place regardless of the run level that is to be entered. And that's why init is programmed to first consult rc.sysinit. So that's the first file that's checked. In addition, init consults the contents of event.d, which includes items for starting and stopping and restarting the system. These are the event-driven config files that upstart is responsible for. And its syntax reflects the following. For example, start on stopped RCS. Now RCS means system initialization. So after the system initialization has been started, or stopped that is, then we start everything else that pertains to starting the system. And the output is sent to the console, and the execution or the process that's run is cklog system start. So this is the event-driven upstart coming into action here. And the converse happens on stop, and a similar combination on restart. So init also consults this etc event.d directory for instructions for what to do after the system has been initialized. In addition, init will then consult the functions file, which is also required by all run levels. That file is located in init.d, and if you have a look at this file, you can get a sense of its purpose. Let's take a look. Init.d functions, and it sets up paths, for example. So this search path is available regardless of who's logged in. In the case of root, that is, this is for root for user sbin. And a number of other variables, default umask, console information, colorization, you name it. There are a number of things that are set in the functions file that are required by the various run levels. So after event.d is consulted, which causes upstart to start its process, then the contents of functions are parsed and set up. Once the etc init.d functions file has been consulted, then the appropriate run level has to be consulted. Now that's determined by the legacy init tab file, which is an etc. So let's take a look at init tab. Traditionally on Linux and Unix systems, init tab contain the items that are processed by init when control has been handed over from the kernel. Now it's still consulted, but it's being deprecated, so it's consulted for less important information. It includes a lot of comments explaining the various run levels, as we've discussed, but the item that's extracted, the only item that's uncommented, is the default run level. So notice it reads id:3 init default. So init reads etc init tab to determine the default run level for this particular system, which happens to be full multi-user mode and can be changed. So it's the only item that's currently referenced from here. However, if you notice above, init tab is fully commented. It reads that init reads rcs.conf, so etc init. This is another directory that's processed to help initialize the system. And then the run levels are started by rc.conf, and control-alt-delete, which was formerly handled by init tab, is now handled by etc init control-alt-delete.conf. And the terminals are handled serial.conf if there are any terminals set up on your terminal, on your serial devices, and so on. So that leads us to the init directory. Let's take a look at init. So things have been spread out quite a bit. There are some conf files in here that are defined to assist in setting up the system. For example, the control-delete function now exists in a separate file. Let's see how upstart processes this. So start what follows on the interception of the event control-alt-delete So when Control-Alt-Delete has been intercepted, which is an event, of course, it's a sequence of keys that are executed that the system knows about, then execute the following: shutdown right now. Basically, Control-Alt-Delete has been pressed, and this is what's echoed. So this is the sort of event, object-oriented, logical, or natural type of processing that Red Hat Enterprise Linux now relies upon. Again, the notion here is when the sequence of keys Control followed by Alt followed by Delete have been intercepted by the system, upstart will recognize that and then execute shutdown right now. So it isn't terribly complex by any means. And there are a number of other items in here as mentioned. How to set up TTYs, for example. So we're always connected to a TTY when we open a shell. So just typing TTY will tell you we're currently at the console, and tty.conf includes config files or config entries. Let's cat tty.conf that upstart uses. So for example, this causes the TTYs to be stopped on the following run levels. So if 0, 1, or 6, well, we've mentioned that 0 is to halt the system, 1 is single user mode, and 6 is to reboot the system. So in the case of either of these, and this is just using standard regular expressions to express either or, so this is an or condition. So if 0, 1, or 6 have been detected by upstart, again, it's event oriented, then it's going to stop the get TTYs that are running. What does that mean? Well, when you halt the system, the TTYs should be cancelled. When you enter single user mode, there should be no TTYs. There should simply be dev console, because remember, TTYs are largely used remotely or to provision multi-user access on the same system physically. So the idea is to restrict access through various terminals, which could cause data corruption. So the event here for tty.conf is to stop the get TTY process in the event of the following run levels, 0, 1, or 6. Let's take a look at start ttys.conf. This one's a little more complex. So it stops on run levels 0, 1, and 6, or that's the tty.conf file. This is the new one. Let's not confuse the interfaces here. Let's retype this. And now this is more like it. So this service starts the configured number of get TTYs. Get TTY or min getty is just a process that will set up TTYs for us. So when you're up in multi-user mode, the TTYs are available, and you can use Control-Alt F2 through F7 to access the various consoles, with one being the GUI, which is also a TTY. So here are the active consoles, TTYs 1 through 6. And the environment variable, dev tty1, and here's a task. It's a script, so it's a number of items that are executed. So init. Now here's a loop. So for tty in the active consoles, which this variable sets to dev ttys 1 through 6 using regular expressions, do the following. And it starts a tty on each of those tty's. So this is just a for loop to loop through the 6 defined tty's. In other words, if you needed more or less tty's, you could just expand the numbers here. Now back to the upstart event handling. Notice above it reads start on stopped RC run level. So this tells us that after the run levels have stopped, these are 2, 3, 4, and 5, multi-user run levels, do the following. So that's the event-oriented nature of this new startup manager or process manager. So it'll happen after those run levels have successfully launched. In other words, bring up the run level. If it's come up successfully, then start the TTYs. Let's take a look at what else is in here. rcs.conf, system initialization, which includes the fact that it's to initialize the system. And as we've mentioned, here's the execution of rc.sysinit. We've mentioned that when init starts, it initializes the system via this particular script. So that's lsl rc.d rc.sysinit. And there's rc.sysinit. Notice that it's flagged executable, and notice that it's also colored green. This tells us that it's executable. So init starts, and it starts sysinit first to initialize the system. And again, we have a condition here that's checked. It's a script. It's a bash shell script, nothing more complex. So the new process still makes use of bash shell scripts. And by the way, this version of Red Hat Enterprise Linux includes the 4.x series of bash. preferred display manager, for example. So in the case that we're using run level number 5, and notice it even reads start on stopped run level 5. So after run level 5 has successfully launched, then we're going to set up the preferred display run level. And notice there's a converse of that. It stops if the run level is not 5. So if you're in run level 5 and you decide to shift to a different run level, let's say 3, or perhaps 1, 0, or 6, then the preferred display manager will terminate. So it sends output to the console, respawns with some limits set, and then it executes X11 preferred display manager no daemon. So it brings it up as a user space process. So pref.dm or preferred display manager.conf is the config file that Upstart reads to determine how to launch your GUI manager or your display manager. So this is etc init, the items that are read from this particular directory. And we've mentioned that there are still run control directories for the run level that you've entered. That hasn't gone away. Let's take a look one level up. We're now in etc. Let's navigate into RCD, and in RCD you'll still see the run level directories. So depending upon the run level in which you've entered, you will cause the scripts in that process based on their kill and start alphabetized or arranged values to execute. So currently we are in run level 1, single user mode. Let's navigate into rc1.d. So this still remains, although Upstart's the new manager. Notice a series of scripts which include kill and start prefixes. Kill scripts are processed before start scripts. That ensures that the processes that should not run in a given run level are terminated, regardless of whether or not they're running. So it's a way to ensure that they're not running for the run level. The kill scripts are processed, and they're processed alphabetically ascending and numerically ascending, alphabetically and numerically. So K01 comes before K02. There are two K01s, so K01 cert comes before K01 smart. All of these kill scripts are run. Then after the kill scripts, the start scripts are run. The other run levels are documented in their respective directories, RCs 2, 3, 4, 5, and 6. The number of kill scripts are in 6, as well as 0 when the systems are rebooted and halted, respectively. So the run control directories are process, and last but not least is rc.local, and that's in this directory. This is a place where you may place programs or processes that are to be executed post initialization. So catting the contents of RC local will give us a sense. This is where you should put programs. For example, programs that don't have typical sysv init run control scripts. It's a place for you to drop the execution of something, let's say a backup agent or otherwise. So rc.local is where you place those sorts of programs, and you can place it as a line perhaps preceded with a comment, and the program will be launched after the fact. So init processes a number of directories, a number of files. It begins by processing rc.sysinit, which etc init and the sysinit or rc.s.conf file instructs it to do. It initializes the system, it reads event.d, it sources the functions file, and it processes the appropriate run control directory, the kill and start scripts. Then it also reads rc.local, and in this case the only entry that's processed from the file is a touch of varlock subsys/local. Once all of this has been processed, the system is basically up and ready to go. So if you take, for example, multi-user rc3.d and you do a search for SSH, this is where SSH is listed as the 55th item to start. Doesn't mean there are 54 preceding items, it's just ordered this way, but SSH starts and it references init.d. Let's just note that as well, that all of these kill and start scripts really reference the initd directory where the scripts live. All the scripts that are to be started and stopped on your system during initialization or shutdown or reboot or halting are located in etc init.D. They're simply symbolically linked or shortcutted from the appropriate run control directory and processed by upstart in conjunction with init accordingly. So that's a little bit about how your system initializes. Again, it's the BIOS, hands off to grub, which handles its two phases, which hands off to init.rd, kernel, init, and then you have access to the system. Init goes through a series of steps to set up the environment for you, including initialization, so rc sysinit, as well as event.d, as well as the functions file, which is in init.d functions, as well as the appropriate run control directory, etc rc $.D, let's say 3 for the default. The contents of etc init are processed, and when the process is finished, it processes etc rcd rc.local, and in the midst, init knows the default run level by reading init tab, so etc init tab, and this isn't in order for the default run level. And that's how init sets up your system after it has been handed control from the kernel, which is the scheduler, which is PID 0. So that's how your system is up and running, and if there's any trouble along the steps mentioned, you should have a sense as to where to look, whether it's the BIOS or grub's inability to start, perhaps because the MBR is out of line, or perhaps your init.rd is a wrong file or it's corrupt, or perhaps the kernel file is the wrong file or is corrupt, or perhaps there's a problem with one of the init files starting up. As mentioned, when you boot in emergency mode, init isn't started, and as a consequence you avoid all of those steps that could prevent your system from booting. So one way you may be able to successfully boot and mount your file systems is to boot into emergency mode. And single user mode boots with a minimal init, so it starts just with the basics necessary to initialize the environment. Again, the run control scripts are in rc.d. Take a look at this directory, and it includes all of the run control items for the various run levels, including run level 1 or single user mode. So that's a little bit about the init process. Let's go ahead and now initiate an init 6. This will restart the system.